Good morning. We are Team CMA Company. Our project is system analysis and optimization of the production line at CMA Company. My name is John Bathel.
And I'm Renee Anguiano.
I'm William Carrion.
I'm Michael Zapata Bulldog, and our advisor is Dr. Brzai.
Here's Willie with our agenda.
Our presentation today will cover the problem statement, the baseline metrics, our process standardization, the current state of the company, alternative solutions and simulations, the economic analysis of those alternatives, and our proposed solution.
CMA Company was founded in 2004 by Terry Downing on his kitchen table as a favor for a friend. When the product went through inspection, it was the highest quality they ever received, and CMA Company was formed. They now occupy a 5,000 square foot facility in Corona, California. CMA Company needs to increase their throughput of their loopback production from 1,142 units to 5,000 units annually, or an increase of 338%. A constraint given to us by CMA Company is that one employee completes the process from start to finish. Michael will now go over the value stream map.
This is the VSM for the baseline state at CMA. The net available time in a day is about 460 minutes. The annual customer demand is 5,000. This results in a takt time of 24 minutes per loopback. The current cycle time is 76 minutes, which means we need to reduce the current cycle time by about 68% or 52 minutes.
From our data collection of the one loopback station, the team calculated a cycle time of 76 minutes per loopback. However, the simulation showed that the cycle time was closer to 88 minutes when we factor in rework and scrap, which the employees chose not to report. Now Renee will cover the manufacturing defects observed.
Thank you, Willie. After collecting the raw data from quality inspection reports, the main defects were related to electrical contacts and loopback finishing defects, such as contacts not fully engaged, contacts in the wrong places, bent contacts or broken contacts, burnt shrink tubing, or too much or the wrong size of a certain material. These defects result directly from the workers and require a large amount of rework if not caught during the process. In order to find the root causes of the production defects, the team created a cause and effect diagram. After looking at the possible causes gathered from interviews and inspection data, the team found that the methods and the workers were the main causes for the defects and rework. From the methods category, lack of planning and deviation from the process were standouts, and from the people category, insufficient training also stood out. Developing standard processes can potentially fix the root causes of these defects.
After observing and documenting the process in detail, this checklist was formed to ensure that steps are not missed or skipped. To combat the lack of planning, a chart was created that removes the guesswork for the employee. There is a correlation with the part number and the length of material that needs to be cut. This allows employees to determine the length of the material that needs to be cut since each loopback is different. This allows a new employee and a seasoned employee to produce the same product. I cannot show the whole chart as the owner has requested that we keep this information proprietary.
Next, we standardize the selection of materials by calculating how many wires can theoretically fit in each size of shrink tubing. The results were then validated and modified by experimentation, which led to the creation of this chart. This chart clearly shows the diameter of shrink tubing required for a set amount of wires and takes the guesswork out of the process. This specific chart covers 22 gauge wire, but there are charts like this for every size wire that is used. To address the insufficient training, the charts were implemented and 3 hours of training were set aside to instruct the employees how to use the new charts and give a refresher on how to build loopbacks properly.
Next, the team looked at the workers' workstations. The picture on the right shows what the workstations looked like when we first arrived at CMA. Stations were cluttered and the required tools were not always within arm's reach. Additionally, each station was different. causing confusion among workers. To fix the workstations, the team implemented 5S lean principles. The team determined what was necessary, found a home for each tool, and cleaned the desk of any dirt and debris. Tools and materials were placed in a standardized location within arm's reach, while important documents were attached to the desk to ensure that they don't get misplaced. The first bullet point shows the common tools required to build that were placed in a fixture within arm's reach. The second bullet point shows the common materials that were pre-cut and placed in a standardized location available for quick and easy access. The third bullet point shows the location of the standardized documents that were taped down to the desk in order to ensure that they do not get lost nor misplaced. Next, Renee will talk about the results from the implementation of these process improvements and standardizations on one loopback workstation.
Thank you, Michael. After implementing these process improvements, the team collected data on the new cycle time and entered those values in the simulation and compared those to the baseline simulation. Cycle time is down from 88.56 minutes to 43.82 minutes, a 50% improvement. We also increased the first pass yield from 95% to 96%, a 1% decrease in rework. Next, the team performed a pair t-test to see if there was a statistical difference between the throughput of the baseline system and the system with process improvements. Since the t-statistic is greater than our t-critical, we reject the null hypothesis because there is indeed a statistical difference between the throughput of the baseline system and the system with improved processes. Even with the process improvements, unfortunately, our goal of producing 5,000 loopbacks a year will not be met with just one worker. Next, William will propose the alternative solutions to meet the demand of throughput required.
This slide shows our alternative solutions to meet the desired throughput. The first utilizes the baseline system with the addition of 4 more stations and their corresponding workers. The second implements the proposed process improvements of the baseline system that will require the addition of 2 more stations with 1 worker each. The final alternative is the implementation of an assembly line process with 6 workers at 6 different process stations. Next, John will cover the simulations corresponding to these alternatives.
The result from our simulation for alternative 1, where the baseline process is used with the addition of 4 workstations and workers, we are able to make the demand of our yearly throughput. The daily throughput is increased from 4.57 loopbacks to 20.7 loopbacks per day, which is an increase of 353%. While this meets our yearly throughput, there is an increase in overhead through the addition of 4 employees to make our goal, which we'll go over in our financial analysis. When evaluating the simulation model for alternative 2, where this alternative uses the improved workstations and processes tested, in this model we increase to 3 workstations and 3 workers. Since the cycle time is reduced by 50%, the daily throughput is increased from 4.57 loopbacks to 27.7 loopbacks per day, which is an increase of 497%. This has a reduction in overhead from alternative 1 and an increase of throughput from 5,175 to 6,817. This allows for flexibility and possible disruptions of workflow or supply chain. The simulation model for alternative 3 was constructed outside the constraint given to us by the company, but is a valid alternative to explore. In this model, we split up the different processes of building a loopback to create an assembly line system. This model utilizes 6 different workstations with 6 workers. The cycle time is reduced by 51% over the baseline. The daily throughput is increased to 32.48 over the baseline of 4.57, which is an increase of 611%. The increase in production does come at the cost of increased overhead. It also greatly exceeds the demand of 5,000 loopbacks a year by 3,120.
We compared the throughputs of the three alternatives to the baseline using pairwise hypothesis testing. Our null hypothesis was that there was no difference between the average throughput of our alternative solutions to the baseline. And our alternative hypothesis was that the mean between the baseline and the alternatives is greater than 16, the amount of improvement needed to make our throughput goal. Alternative 1 failed to reject the null hypothesis because there was no statistical difference between the alternative and the baseline system because they are essentially still the same system. Alternative 2 and 3 both reject the null hypothesis and seem to be the better of the three systems. Now Willie will talk about the economic analysis.
Our economic analysis for this project was done using the cost of system assets, which in this case is the cost of a station, the annual maintenance per station, the station salvage value, and the annual labor cost per worker, as well as the profit generated in each system alternative. The company already had the necessary capital for 2 of the 3 possible solutions. Utilizing this information, as well as the expected life of the necessary equipment, which is 10 years, and the company provided interest of 10%, we calculated the present worth of each system. In doing so, we found that financially the second alternative was the optimal solution. Based on both the economic analysis done and the simulations of each alternative, the correct solution is the second alternative with 3 stations with 1 worker per station. However, after our analysis, we have a couple of recommendations. The first recommendation is to vertically integrate the supply chain to reduce possible hiccups. Our second recommendation is if demand approaches 14,000, CMA companies should convert to an assembly line, and the data to support this can be found in our report. We'd like to give a special thanks and acknowledgements to Dr. Mirzai, Dr. Placencia, Dr. Falafini, and Dr. Abudini, as well as to Terry Downing and the employees of the CMA company.
We would like to thank you for your time, and do you have any questions?